So hello everyone. Today we'll be starting with the lecture 3 of the first week, where we'll discuss the solution of the LTI systems. So in the last lecture we saw the solution of the linear time varying state space system, both in the continuous time domain and in the discrete time domain. We also saw some properties and implication of these solution in terms of some properties of the state transition matrix and its relationship between the state space parameters and the impulse response. So proceeding with the LTI systems in a similar way what we had done for the time varying systems, first we consider the homogeneous case. So the homogeneous case where we said explicitly that u is equal to 0. Now we are considering only this part. The only difference between the time varying case and the time invariant case, that here the state matrix, this A, is now a constant matrix. Okay. So recalling the Piano-Baker series, what we had introduced for the time varying case, because the time varying case is basically a generic case. Now the idea is whatever the solutions we had seen for the time varying case, we would specialize those solutions for the time invariant case, right? So the unique solution to this equation is given by this part, right? Where phi t comma t naught is the state transition matrix of n times n, and this in this Piano-Baker series, all these A matrices are now the constant matrices. Okay. Now let's consider the kth term of this series, the kth element of this series. So I would have, so this is the 0th element, because if this is the 0th, 1th, 2nd and the 3rd element. So if we consider the kth element, I would have the outer integral from t0 to t, just subsequent integral from t0 to t1, and the last integral would be t0 to tau k minus 1. Similar to if we see the third element, it is from t0 to tau 2. Okay, so this is k minus 1th part. So here in the third element we have a to the power 3. So for the kth element I would have a to the power k, and similarly all these d tau k minus 1 up to d tau 1, right? Now this kth element I can write as the ratio of t minus t naught to the power k and k factorial into ak. The reason is that all these ak are constants, first of all. So I can take this ak outside this integral, and all the inner integral are basically the integrals of the 0th power of t. Okay, so it would turn into t1 minus t naught to the power k divided by k factorial, right? So we can take one specific case. Let's say we want to consider for k is equal to 1, right? Just to better understand the kth term, let's consider k is equal to 1. So k is equal to 1, basically it's this term. Okay, if I put k is equal to 1, the solution would be t minus t naught 1 over 1 factorial into a. Okay, now notice here this part, that since a is the constant matrix, I can take it outside the integral. It would be t naught to t d tau 1, and this one is basically given by t minus t naught, and this part is basically equal. Just for the better visualization, you can also consider for k is equal to 2, k is equal to 3, just to understand that the kth term or the solution of the kth term would be given by this one, right? So if I sum all these kth term starting from k is equal to 0 to infinity, because these are all the summations, because of this summation, if I sum all these kth elements starting from 0 to infinity, I would actually get the closed form solution of the state transition matrix, which is equal to the summation over k is equal to 0 to up to infinity of this part. Okay. Now let's see some interesting thing of this state transition matrix. Okay. So first of all, we'll define the matrix exponential of a given n cross n matrix M which is given by e to the power m is equal to the summation of, basically this is a series. Since this is an exponential, it would be summation over k is equal to 0 to infinity 1 by k factorial into m to the power k. Okay. Now using this exponential, if I try to rewrite this part, I could write phi t comma t naught is basically the exponential of a t minus t naught, right? So if I replace m by 8 into t minus t naught here, let's say replace m by 8 t minus t naught, I would have summation k is equal to 0 to infinity 1 over k factorial, and m is basically a t minus t naught to the power k. Right, which I can write a to the power k into t minus t naught to the power k, which is equal to this part. So my state transition matrix in the linear time invariant case is basically the matrix exponential, where t naught is the initial time where I am taking the initial value of the state. Okay, coming on to the non-homogeneous case, where we are now using u also. So this u would have the similar effect what we had seen in the linear time varying case. This is the state transition matrix phi. This is also the state transition matrix into b into u. So if we go through the solution of the LTI system and I replace those state transition matrix by this matrix exponential, I would get the same solution for the x and for the y as well. Okay. Now there are certain interesting properties of this matrix exponential in a similar way for the LTI case, that if e to the power at is the state transition matrix, we know that the state transition matrix is the solution of this part. If you recall from the LTI case, that phi dot of t comma t naught is basically given by at phi t comma t naught for the LTI case. Now phi dot t comma t naught is basically is e to the power at, the matrix exponential, the derivative of this matrix exponential. In this case we have a as a constant matrix and e to the power at is again the state transition matrix. So the first property remains similar to the LTI case, where we just replaced the time varying state transition matrix by the matrix exponential. Again, for every t comma tau belongs to R, we can write the multiplication of matrix exponential at t and at tau by the matrix exponential at t plus tau. Okay, we should also remember that if I am computing the multiplication of two matrix exponentials at the same time but with different matrices, okay, this is not equal to the summation of that matrix exponential. Okay, this is possible, or I would say this is equal to this one only if a, b are scalars. Right, here we have a, b as the matrices. Now for the third property says that for every t belongs to the set of real numbers, e to the power at is non-singular, and it satisfies this part, that the inverse of the matrix exponential is given by the negative power of the matrix exponential. The fourth property, that for every n cross n matrix A, the multiplication of A, that I can compute this multiplication of the matrix A and the exponential matrix with matrix A. Okay, the proof of this part you can do by yourself. The hint is that you can first of all use the series of the exponential series and then multiply with the A, pre-multiply and the post-multiply with the A matrix. Now the computation of the matrix exponential, So we know that E of AT is uniquely defined by this relation. By using the first property of the metro exponential, we can compute the function. So taking the Laplace transform both sides, we would having the Laplace transform this part and the Laplace transform this part. Of this part, we denote S into the Laplace transform of this function. So this is denoted by the hat. Okay, minus the value of that function at t is equal to 0. Okay, basically the idea here is, if I have a function f of t and I want to take the Laplace of f dot of t, it is given by s of fs, excuse me, s of fs minus f of 0, and this f of s we have been representing as f by a hat, just to denote that it's a frequency domain counterpart of the time domain function. This is what we have represented, this notation what we have used here. Okay, similarly here, since A is a constant matrix, I can take it outside of the Laplace transform, A into the Laplace transform of this function. Taking this part onto the left hand side and this one onto the right hand side, I can write this part Si minus A into the Laplace transform of e to the power at is equal to y. And finally, I can write the Laplace transform of the metro exponential by Si minus A inverse. Okay, so simply by taking the Laplace inverse of this part, I can compute the time domain metric exponential. Okay, now there are some interesting properties of this Si minus A, which reveals some internal structure of the state space system. So this the inverse of Si minus A, I can write as the ratio of the transpose of the adjoint of Si minus A divided by the determinant of Si minus A. Now this determinant of Si minus A can be given by this one, where all these powers. So what I have done here, this Si minus A, if I take the determinant, it first of all it would be a polynomial, right? Now when it is a polynomial, I can factorize into the lower order polynomials. Here we are taking the first order polynomials, which could have their multiplicity greater than equal to 1. Okay, greater than 1. So here we are taking m1, m2 up to mk. Okay, so this denotes the characteristic polynomial of A, and all these roots, if I put it equal to 0, then I would, all these roots lambda 1 up to lambda k or the lambda I are all defines the eigenvalues of A. Okay, now the idea of denoting this m1 and m2, meaning to say that there could be two eigenvalues at the same location. Let's say all this part is equal to 0. Oh sorry, all this part is equal to 1. Okay, and here we have m1 is equal to 2. It means that we have two eigenvalues at lambda 1. This is the reason we are defining this multiplicity. Okay, now this adjoint Si minus A is the adjoint matrix of this matrix Si minus A, whose entries are polynomials in S of degree n minus 1 or lower. So we know that if our A matrix is the n cross n matrix, then this polynomial, which is the determinant of this part, it would be having the degree n. Okay, but when we take the adjoint of Si minus A, it would always have the degree up to n minus 1. Okay. So to compute the Laplace inverse of the Si minus A, we do the partial fraction, which could take this form possibly. That here we write the determinant, the characteristic polynomial, right? And here we take the order up to n minus 1. Depending on all these coefficients, this order could be lower than the n minus 1. Right? Now if I do the partial fraction for only this part, s minus lambda 1 of power m1 this would be the partial fraction with all the coefficients which are need to be identified. Right? Similarly, all these lower degree polynomials of multiplicity mi, I have individual parts. Okay. Now if I take the Laplace inverse, it would have a11 e to the power lambda 1t plus this a1 m1 t to the power their multiplicity minus 1 into e to the power lambda 1t. Similarly, for all these lambda i's up to k, starting from 1 to k. Okay, now suppose if all the m's, all the mi's are equal to 1 for I is equal to 1 up to k. Okay, we won't be having this term because if I put m1 is equal to 1, it would be 0. So the only remaining term is this one. Now see that when all the eigenvalues of lambda I of a have strictly negative real parts, then all entries of e to the power at converge to 0 as t tends to infinity. That is, the response y of t would converge to the forced response given by this equation. Okay. Now talking about the discrete time system. So there are some couple of interesting facts. So we know that most of the real world systems are continuous time system. And we saw in the time varying case that the solution of the discrete time system is basically easier to compute than what we do in the continuous time systems, because we can compute the state transition matrix recursively. Right? So the first approach is either we discretize the continuous time system or we directly use the discrete time system. So let's say given a continuous time system, what are the different methods, or how, first of all we would see how we can discretize that continuous time system. So say for example, given the continuous time system by this part, the straightforward approach for discretization is to approximate this x dot t by this part where t is the sample time. Okay, xt, so we are approximating this derivative by xt plus capital T minus xt divided by capital T. So whenever this capital T approach to 0, this part would become the x dot t. Okay, so now if I put this part, this equation into this equation, I would have xt plus t equal xt plus axt capital T plus but capital T. I just put this part into this equation. And further, for simplicity, we can write that if we are computing the xt and yt only at t is equal to kt, where t is my sample time and k is the sampling instance. Okay, starting from 1 to t up to the infinity, then I could write x of k plus 1 into t is equal to, if I combine these two parts, it would give me I plus ta into x of kt plus tb into u of kt. Similarly this part. So this matrix is defined as the discrete time A matrix of this continuous time A matrix. Okay, this is BD. Let's denote the D as a discrete time B matrix. Okay, there won't be any effect on the C and D matrices of in the discrete time, which are remaining similar to the continuous time matrices. Okay, but this discretization, since we saw that it is quite easy to carry out, but yields the least accurate results for the same T. You can verify this in simulations also by taking different values of T and taking any scalar system. You can take any scalar continuous time system, and by using this approximation, try to compute the discrete time values and see whether the values at discrete time instance matches with the continuous time values. Okay, so there is another method which is much more efficient of the discretization, where we suppose that our u of t is basically is equal to u of kt for t lying between kt to k plus 1t. Okay, this means that I am considering u is a piecewise constant signal. Say for example, if let's consider this time axis. Time axis, this instant is my kt and this instant would be my k plus 1t, that is my sample time in the kth instant. So whatever the value I am having here of this u, I am keeping it constant up to the next sample. Now if I move towards the next sampling instant, let's say it is having this value, so I will keep it as a constant value up to the, so this part would define the k plus 2 times t. Okay, now since this is a continuous signal between the two sampling instants, so I can use the continuous time solution to write the solution of the, or between the to write the solution between these two sampling instants, right? So let's see. So I compute the solution at t is equal to kt and also at t is equal to k plus 1t. So this solution is given by, I am using this denotation in the square brackets just to explicitly denote that we are dealing in the discrete time. Okay, so we are having this x of k which is equivalent to x of kt. We can remove the sampling time once it is fixed for all the computations. So here I replace all t by kt's, right? E to the power at x naught starting from 0 to t replaced by kt, and similarly this part. So this is the solution of the continuous time state equation at t is equal to kt and at t is equal to k plus 1t. Okay, now let's see. So first of all, I break this integral into two parts. This integral starting from 0 to kt, which is this one, 0 to kt, and from kt to k plus 1t. Okay, now from the break integral from 0 to kt, I take this part metric exponential as a common from this one and from the break integral, which I can write e to the power a kt, because if I take e to the power at common, the only remaining part is this one, into x naught plus this part, because this part would also, I can take it outside the integrals, because since this is a constant for this integral, because this integral I am taking over tau. Okay, and the other break integral from kt to k plus 1t remain as it is. This is k plus 1 into t minus tau. Okay, now pay attention here that this part is nothing but equal to this one. Right? We have e to the power kt x naught, e to the power at x naught, and this term also is equal to this term. So I can replace this whole term by x of kt. Okay. So I substitute this 12 and 13 into this equation to finally write x of k plus 1 is equal to e to the power at into x of k, which is this one, plus this integral 0 to t e to the power a alpha d alpha into duk. Okay, because I replace this part by alpha, so I would have e to the power a alpha d alpha, because b, since b is a constant matrix. Okay, and then rearranging these, the lower limit of the integral and the upper limit of the integral, we finally got this expression. Okay, now let's see. So this part I can define now the discrete time A matrix of the continuous time system, and this is, and this whole part, basically this whole part is the BD matrix. Let's see in the next slide. So we have xk plus 1 is equal to e to the power at xk plus this one, so which I can write into the discrete time state equation as AD and BD, CD and DD, where AD is now equal to e to the power at and BD is this whole expression. The C and D matrices do not change. Okay, now basically it should be e to the power a into capital T, right? Because we are having e to the power at. Given the sample time, we can compute this matrix exponential. Okay, here for the computation of BD, we need to compute this integral, right? But we also have a, a solution for that. That instead of computing the solution, we can write the closed form solution of this one. So first of all, seeing the computation of BD, note that if I take given this series, right? Given this series, and I take the integral of this series from 0 to t, I can write this one. The first one would be t, right? It would be a t square by 2 factorial. Similarly, this one. Okay. Now, if a is non-singular, then this series can be written as I multiplied by this a inverse. Okay, multiplying by this a inverse would give me this part. Since t is a scalar, so I can commute. Right now, at the end, I do the addition and the subtraction of the identity matrix of appropriate dimension. Okay, now see this part. Now this part is basically equal to the matrix exponential e to the power at. Okay, and this e to the power, so this part would become e to the power at minus I pre-multiplied by the inverse of the A matrix, and this e to the power at is basically my AD. So I can write the discrete time B matrix as A inverse multiplied by AD minus A into B. So once I have computed the matrix exponential to compute the discrete time A matrix, I can directly compute the BD matrix instead of computing the exponential, the integral of that exponential. Okay. Now the same discretization you generally see in the MATLAB function when you do the continuous to discrete time. This is the MATLAB code. You can take any A, B matrices given a sample time capital T. These A, B matrices are the continuous time matrices. Now if I use this function to convert or to transform the continuous to discrete, it would give me AD and BD. If you compute for the given AB matrices using this equation and this equation, you would get the same result. Okay, so this is the most accurate discretization. After seeing the discretization, let's come on to the solution of the discrete time equations. Say for example, if we are directly given the discrete time systems, we know that both these equations are the algebraic equation, and one direct way of computing the solution is to do recursively. Once x0 and u of k are given, for k is equal to 0 to up to the current time are given, the response can be computed recursively from these equations. Now the interesting point here is that now we see the explicit significance of the initial condition and all the u's starting from k is equal to 0 up to the infinity. Say for example, if I put k is equal to 0, k is equal to 0 in this equation, I would get x1 is equal to ax0 plus bu0. Let's put k is equal to 1. I would have x of 2 is equal to a into x of 1 plus b into u of 1. I can write x1, I can replace this x1 by this x1 to finally have a square into x0 plus ab into u of 0 and b times u of 1. So I can parameterize all the solution of the state equation in terms of the initial conditions and the u of k for all k starting from 0 to up to the current time. Okay. Now proceeding forward, we can readily obtain for k greater than 0 is this part. Okay, and the state transition matrix phi of k comma k naught is given by the k minus k naught power of a for all k greater than or equal to k naught. Okay, this you can, once you start doing for the kth time, you will finally approach towards this solution. Say for example, if I put k is equal to 2, just for the better visualization, in this part, let's say if I put k is equal to 2, because we already have the solution for k is equal to 2. So we would have x of 2 is equal to 2. If I put k is equal to 2 here, and this part would be summation m equals 0 to 1, k minus 1 1, and then a 1 minus m, b u of m. Now here in the summation I would have only two terms for m is equal to 0 and m is equal to 1. So if I put m is equal to 0, I would have a into b into u of 0, which is this term. If I put m is equal to 1, this would be identity b into u of 1, which is this term. So you can validate also for other values of k. Now just putting this xk again back to here, we get the response, which is basically the summation of the two individual responses, one because of the initial state and another because of the input. This is the zero input response and this is the zero state response, where the state transition matrix is given by this one. Now coming on to the computation of the state transition matrix. So here the matrix power can be computed using Z transforms. So for the continuous time we use the Laplace transforms. For the discrete time we would use the Z transform. So we need to compute the Z transform of a to the power k plus 1. Okay, this I can write by this expression Z to the power minus k into ak plus 1, where k is from 0 to infinity. Okay, now see here, if I multiply and divide this expression by z, I can take z outside or inside of the summation, because I am taking the summation over k, not over z. So z is a constant for this summation. I multiplied by z and divide by z, I would get z to the power minus k plus 1 into the rest of the part, that is a to the power k plus 1. Okay, now see interesting thing here. Let's say I represent k plus 1, I replace k plus 1 by some variable t. Okay, now this one would be given by z, excuse me. So at k is equal to 0, I would have t is equal to 1, the lower limit, and the upper limit would be infinity, right? Here I would have z to the power minus t and a to the power t. Okay, now here I need to include this k is equal to 0. So let's say the value of this summation at t is equal to 0. The value of this at t is equal to 0 would be what? Identity. So I add plus I and subtract I, the identity matrix of appropriate direction. Now this part I can write as this one, where I have changed the lower limit of the summation from 1 to 0. Okay, so this summation is k is equal to 0 to infinity. The rest of the part would remain the same, minus I into z. Okay, so I can write this expression as z times the z transform of this a to the power k minus I. Okay, and also we know that the z transform of a to the power k plus 1, I can write this one because a is a constant. So I can take the a outside of the transform. Okay, now in a similar way, if we proceed, this a is this one, and this z transform of ak I represent by a hat. So the hat of the a to the power k over hat is basically the Z transform of AK. So after simplifying all this part, I finally get this part, that the Z transform of A to the power K is given by Z times the inverse of Zi minus A. Okay. So taking inverse of Z transform, we obtain the A of K as the Z inverse of this whole part. Okay. Now similarly, if all the eigenvalues of A have magnitude smaller than 1, because all the eigenvalues should lie inside a unit circle, then all entries of A to the power K will converge to 0, as basically it should be K tends to infinity. Okay, which means that the output will converge to the force response, right?